Hello everyone, welcome to Physics Mage. Today we have a good problem which tests your understanding about electrostatics of conductors, like about charge distribution and redistribution, uniqueness theorem, etc. So let's try and apply our concepts. Consider a thin conducting shell of radius r carrying a total charge q. So this shell is carrying a charge q. The 2 point charges q and 2q are placed on points A and B. There is one charge here, q, the another charge here, which is 2q charge, which are at distance 0.5 r and 2r from the center C of the shell respectively. That's already given here. If the shell is earthed, how much charge will flow to the earth? Switch here. Suppose if we switch on this one, then how much charge will flow from the given shell to the earth is the question. Okay. Based on our understanding, I hope you're all familiar with this idea that if we have a charge exactly at the center, suppose q amount of charge is placed at the center, and if we connect this to the earth, then you know that the shell will have the same voltage as that of the earth. So 0 volt is the voltage of that particular conducting shell. Yeah. Now, if that is the case, if we want to have electric field to be zero inside the metal conductor, meaning metal muscle, okay, there if we want field to be zero, then the charge should be induced in the interior surface, and that charge will come from the earth to the interior surface. So it has to be exactly Q minus Q, which is induced charge, and this minus Q along with this Q, the charge enclosed inside our Gaussian surface. If you drop one Gaussian surface passing through this metal muscle, that will enclose zero charge. So we know that field at any given point inside this metal conductor will be zero. From the symmetry rules, probably you know this. And since we are connecting it to the earth, we also know that potential is zero at every single point inside this conductor. Now suppose instead of having a charge exactly at the center, let's place our charge bit offset from the center. What happens now? Still we have this earth being connected to the conductor. So we ensure that the so-called conductor will be in 0 volt state. The field inside the metal muscle would be 0, and the voltage at every single point inside this conductor will also be 0. The interior surface should carry negative charge in the inner surface, but this time the charge will not be symmetrically distributed. It is like asymmetrically distributed. But even though this is the case, the charges will distribute in such a way that field should become 0. First of all, why these charges are distributed in a particular way? As soon as we move this particular charge, the field inside the metal should become 0, right? Or else it will not be electrostatic condition, so the charges will redistribute. I hope you're all familiar with this idea. So as long as we are moving the charge inside this one, then the charge in the interior surface keep organizing itself to ensure electric field at every single point inside the conductor to be 0, inside metal muscle to be 0. And since we are connecting it to the ground, the potential should be 0. So what is the takeaway from this? As we place this charge, there will be minus q charge induced in the interior surface. As we move this charge at any given point inside conductor, the negative charge here will organize itself. So field would be 0 and potential will also be 0 as we are connecting it to the earth. So when we compute potential at any given point inside the metal muscle, so we don't have to worry about the charge potential contribution from this charge or minus q charge. So that is one thing which we should know. Let's take another scenario where we have a coordinate system. You can call some axis x, y, z. Yeah. Then this is an imaginary surface. Okay. So we call this one as imaginary sphere. Imaginary sphere. Let's say. Now our intention is I want to create a situation which is similar to what is asked in our question. Okay. So let me place one charge here. That charge is q. The other charge which we are considering to be somewhere here, let's say that is q dash. So why are we doing this? Suppose if we have a charge q here and q dash here, our intention is, can we get a configuration where at every single point on this imaginary sphere, every single point on this imaginary sphere, that should turn out to be having zero potential. Can we have such a kind of charge q and q dash relationship is the question. Okay, so for that, let me make it more general. So we will take first a random position point p, and we'll drop some position vectors to that point. Let's say this point p is chosen outside the imaginary sphere. Let's say our sphere has the imaginary sphere has a radius r, and capital R we are using. And let's say position vector from the center, from our coordinate system to that location, right? Let me take it as R. So we can write R vector equals magnitude and direction. Then from Q dash vector, from Q dash position, from Q dash we'll drop one position vector. That, let me call it as some fancy R vector. Let's say R vector dash corresponding to Q dash. Then from Q to P, let's drop one more position vector like that. That becomes our R vector, just R vector, fancy R vector. Okay, so this is the given story. Let's take the position vector Q dash with respect to our origin as this. Let's say this vector is vector B, and another vector we will use for giving location for q with respect to our center. So let's take that one as vector a. Now here, what is vector b? Vector b is the location of q dash with respect to our origin. It has magnitude b and direction, let me call it as n cap, some direction. Okay, and vector a is having magnitude a and direction n cap. So all we are considering here is that the two charges are in the same line. The so-called q and q dash are in the same line. That is our consideration. Now going further, what is the potential at a point P? Potential at the point P. We know that this is just potential at a given location R from the origin, and that has to be like how much? K times q is at a distance r vector, right? So let me take r vector, fancy r vector, magnitude of that, then k times q dash by r prime. Okay, that magnitude. So here I'm just using superposition principle, like from q, like potential offering at the point p, and q dash potential at the point p. Now let's try to write it in other way. We have k q by vector r can be written as, we can write it as smaller, regular smaller minus of vector a, then plus kq dash by vector r prime, fancy r prime, right? That is equal to vector r minus of vector b. If we can write like this, then little bit of rearrangement. So k q by, I'll be taking r outside, writing this r and a vectors in its magnitude form and taking r common. This becomes r cap minus a by r times n cap. Then we have plus k times q dash divided by b. I'm taking outside here. Then we have r by b times of r cap minus of n cap. So I hope you got this one. If you have any doubts, just pause for a moment and see like how things are. And if you're okay, then we can continue. So this is what I'm rearranging here. Now with this, the idea is very, very simple. I want at every single point on this imaginary sphere, the potential should become zero. Meaning, if I substitute potential like small r being equal to capital R, the potential should turn out to be zero. Okay, so using that logic, I will have KQ by capital R here, and this is R cap minus A by capital R N cap plus KQ dash by B into R by B R cap minus of N cap. So this is what we have, guys. Now we will recollect one idea called uniqueness theorem. So I hope you would have heard about uniqueness theorem. So what does it say? Because we are going to ground this so-called sphere conducting shell such that at every single point on this sphere, the potential should be zero. Now we are trying to find a kind of equivalent situation where when we place a charge q outside, there will be an induced charge on the surface of the shell, right? That is as good as placing a q dash amount of charge at some location b vector from the center. So it will give exact same effects such that the potential at every single point on the shell will become zero. That is uniqueness theorem here. Meaning if we can able to predict that q dash, that is nothing but an induced charge on the shell. Okay. So for that, first of all, we need to find some way where that potential becomes zero. Meaning our RHS here should become zero. Suppose if we choose q by r equals q dash by b, let's say minus, then we can get RHS being equal to 0 provided certain conditions should be met. Okay, so I am choosing like this, and here in order to make this quantities, like we want r cap minus a by r n cap, that should be equal to r by b r cap minus n cap. This should become equal here. So how can we make this to equal is the question. So r cap is in which direction? The position vector direction. This one. This is r cap direction. And our n cap direction would be some random direction that we are choosing here. Okay. So let me highlight that. We have our n cap direction in this way, n cap. Okay. Suppose if I consider the angle between them as theta. Theta is the angle between r cap and n cap. So if we choose that as the angle between n cap and r cap, is going to be r cap minus a by r n cap. That magnitude would be root of 1 squared plus a by r the whole square, then minus of 2 times of 1 times of a by r cos of the angle between those two vectors. Actually, it will be plus 2 1 a by r cos of 180 minus theta we'll get. That would be the angle between minus n cap direction. This would be minus n cap direction, and angle between them is 180 minus theta. That when you substitute in a regular formula, you'll get it as minus cos theta there. Okay. So here, if we think of the other term, r by b, r cap, minus of n cap, the magnitude of this is going to be r squared by b squared plus 1 squared. Let me write r by b the whole squared, 1 squared. Then again, on the same lines, r cap minus n cap. The angle between them is cos of 180 minus theta. So it is minus of 2, 1 r by b cos of theta, right? Now, if we want this to be same, then we know that by just comparison for the between these two equations, we'll get to know that by choosing a by r being equal to r by b, we can ensure that these magnitudes are same. Okay, so which means what? We can have our RHS being equal to 0 by choosing a by r equals r by b. Also, q dash equals minus of q by r times of b. So a little bit of arrangement, we can write it as minus q. In place of b, I'm going to use this equation and write r squared by a. So r by a. So this is the q dash charge that I have to place here. And if we place a q dash charge here, which is a negative charge, I will ensure that every single point on this imaginary sphere, the potential will go to zero. Okay, so this is some way where we are able to get potential at every single point on this sphere to be zero. So what is the takeaway? Suppose if you take our conducting shell, metal shell, we actually have a problem like this. We are placing one charge q. Because of this positive charge, there will be induction of negative charges here. Non-uniform induction of negative charges will happen. Okay, such that the potential in our story, we are connecting this to the earth, right? So we need every single point on the shell, the potential should be zero. So normally computing potential at this point because of this induced charge becomes too hectic, right? Meaning we can't solve it just by taking some dq and integrating and all. Meaning this induced charge, right? That negative charge is as good as imagining that we place a induced charge, equivalent charge q dash at this point, which is b distance away from the center, so that this gives exact same effect as if that induced charge will provide. So this induced charge is as good as your q dash. So actually this has some name here, and this we call it as an object, and q dash is considered as image. So you will be recognizing this as a kind of method of images, of solving problems. Probably you might have heard about this. What you have to understand here, this q dash is the induced charge, and which is equal to minus of q by distance. We had distance as a, and radius of this particular sphere is r, capital R. Okay, so as a, meaning if the charge moves closer, then a decreases and induced charge will increase, and as q moves away, a increases, q will decrease, and that is expected about the q induced. And this q induced will increase, decrease, that depends upon the supply of charges from the earth to the conductor and from the conductor to the earth. Okay, so this is the basic logic here. You have to know this to solve the given problem. We'll go back to our original problem. So we have a charge q which is placed at a distance r by 2, and this is r. We have a charge q already given to this sphere, spherical shell. Then there is another charge placed at a distance of 2q from the surface r distance away. Okay. Now, what would be the initial configuration? In order to have the net field inside the metal muscle to be zero, right? For that, minus q charge would be developing in the interior surface of the shell. So the consequence, there will be a plus q charge, meaning 2q charge will be on the exterior surface. Exterior surface, there will be 2q charge. Okay, now we also learned that this q and minus q will have nothing to do with the potential on the surface of the shell. So we will just ignore the contribution of these two fellows for that. Okay, because as we ground this, we don't have to worry about these two charges which are inside it. Okay, one is inside it, the other one is interior. We are going to ignore it. Now, what is the role of this 2q charge? So 2q charge is at a distance r away from it. So this 2q charge usually will produce electric field which passes through this particular material. But to avoid that field entering into the metal muscle, the negative charges will be induced here, and that would be non-uniform induction. Okay, this induced charges here, that is given by minus of q by the formula, the distance of that 2q charge from the center, which is 2r distance, and the radius of this fellow, that's r. So meaning what? The induced charge is going to be minus q. Okay, so now we understood that the induced charge, if this is grounded, okay, in order to have zero potential, the induced charge must be minus q. If induced charge to be minus q, initially it will have 2q charge, correct? Initially it will have 2q charge. Now it has to become minus q charge, meaning from the conductor to the ground, 3q charge should be flowing. Okay, so in our problem, option B will satisfy this condition. So dear students, I hope you understood this problem, and if you have any doubts, please put that in the comment section. Thank you everyone.